Hello everyone, good morning. Today I'll be talking about the corneal anatomy, physiology and wound healing. Now this is the first video in this series of mine and this video is based on the book Yanov, right? So this is the cornea. It is basically a transparent structure which is the transparent anterior wall of the globe. Now with the tear film, the cornea is the major refractive surface of the eye and provides about two-thirds of the total refractive power of the eye. Okay. Now it provides structural integrity for the anterior part of the eye and it's a key barrier against the major infection that may enter in the eye. Now talking about the introduction, the cornea is prolate in shape. Prolate means it is flatter in periphery and it is deeper centrally. Now this is an oblate shape, this is a spherical shape, and now this is a prolate shape which is flatter in periphery and it is steeper centrally. The horizontal diameter of cornea is about 11.5 to 12 mm and is about 1 mm greater than the vertical diameter. So the vertical diameter is about 10.5 to 11 mm. The anterior refractive power of the cornea is about 43 to 43.5 diopter. And as I have already said, it is about two-thirds of the total refractive power of the eye. Now talking about the embryology, the anatomy and the physiology of the cornea. The cornea is derived from surface ectoderm at about 5 to 6 weeks of gestation. It is non-keratinized, it is non-secretory, stratified squamous epithelium. It is non-keratinized, it is non-secretory, stratified squamous epithelium. The tear-air interface, it together with the underlying cornea, it provides about roughly two-thirds of the total refractive power of the eye. As we have read previously, the value is about 43 to 43.5 diopter. The mucinous portion of the tears, which forms the undercoat of the tear film and is produced by the conjunctival goblet cells. As we all know, the tear film has lipid, then aqueous, and then the mucinous part. Right, these are the three layers of the tear film, the lipids, the aqueous and the mucinous part. So this mucinous part is produced by the conjunctival goblet cells. This aqueous part is produced by the lacrimal gland. This lipid part is produced by the meibomian gland. Right? So this is produced by the conjunctival goblet cells. It interacts closely with the corneal epithelial glycocalyx to allow hydrophilic spreading of the tear film with each blink. Right? We'll see it with the help of a diagram. Now this is cornea. This is cornea. Now this is the superficial cells of these are the superficial cells of the cornea. These are the wing cells of the cornea. Below these are the basal cells of the cornea which have the capability to divide. And this is the basement membrane. This basement membrane is basically secreted by the basal cells. Just keep this diagram in mind, it will help you a lot. Right? Now if we see this thing under the microscope, although this is also a microscopic picture, but if we see a more modified view, so these are the apical microvilli. These are basically the projections. Now these projections increase the surface area of the superficial basal cells and this is covered by this glycocalyx layer. Now what is the purpose of this glycocalyx layer? This glycocalyx layer, it converts the hydrophobic surface into a hydrophilic surface. Now, if the surface would not have been hydrophilic, there would not be equal and a smooth spread of tears on this surface, which is very important. So this glycocalyx layer, it converts the hydrophobic surface into a hydrophilic surface. The complete turnover of corneal epithelial cells, it occurs in about 7 to 10 days. The most superficial cells of the corneal epithelium, they form an average of about 2 to 3 cell layer of flat to polygonal cells, as we have seen in the previous diagram. That is 2 to 3 layer thick. These apical membrane projections, they increase the surface area of contact and adherescence between the tear film's mucinous undercoat and the cell membrane. Now laterally, the adjacent superficial cells, they are joined by barrier tight junctional complexes. This see now if these are the epithelial cells, and these are joined by the junctional complexes, the tight junctional complexes. So what they do, they restrict entry of tears into the intercellular spaces. Now there is a free flowing water. So water will enter inside the cells or between the cells. But since there are tight junctions between them, so the water which is above it cannot enter into the cornea. Thus a healthy epithelial surface, it repels dyes as if it is or like fluorescein and rose bengal. But if there is an abrasion, like see this is cornea. Now this is an abrasion. So this thing, what will happen is that this thing will be filled up with the fluorescein dye and we call it a stain positive. Now beneath the superficial layers are the supravasal or the wing cells. And this layer is about 2 to 3 cell layers deep and possesses similar tight lateral intercellular junctions. Now beneath the wing cells are the basal cells. Now these cells are very important and we need to know something about them. They comprise the deepest cellular layer of the epithelium. This is a single cell layer. Keep in mind, this is a single cell layer of columnar epithelium, which is approximately 20 micrometers tall. Now, beside the stem cells and the transient amplifying cells, the basal cells are the only epithelial cells capable of mitosis. So they divide and they form the supravasal or the wing cells, the superficial epithelial cells, and so on. Now beneath the basal cells we have a basement membrane. So the basal cells are attached to the underlying basement membrane by an extensive basal hemidesmosomal system. Right? Now this attachment is very important. Why? Because it prevents the detachment of the multilayer epithelial sheet from the cornea. Now this is the base. Now these are the 20 micrometers tall basal epithelial cells. And this is the underlying basement membrane. And this attachment is by the hemidesmosomes. Now, why these hemidesmosomes are important? Because they prevent the detachment of the multilayer epithelial sheet from the cornea. Now, what will happen if there is any abnormality in this bonding system, an abnormality in this thing? So it may result clinically in either recurrent corneal erosion syndromes or in persistent non-healing epithelial defect. Now this basement membrane, this blue structure is composed of an extracellular matrix material which is secreted by the basal cells. Now these basal cells, they secrete this basement membrane. Okay. Now following destruction of the basement membrane, about 6 weeks are required for it to reconstitute and heal. The epithelial bond to the underlying newly laid basement membrane, they tend to be unstable during this week period. Unstable and weak during this period, which is about 6 weeks. Okay, so during these 6 weeks, a patient is prone for the development of recurrent corneal erosions and non-healing epithelial defect or a corneal erosion after a minor trauma. Coming on to the important, the X, Y, and Z hypothesis. Now the epithelial stem cells, they have been localized to the limbal basal epithelium. See if this is the cornea. Sorry, it's not a circular one, but on the periphery of it, 360 degree are the limbal stem cells. Right? So the stem cells, they have been localized to the limbal basal epithelium. Now, as the cells migrate to the central cornea, they differentiate into the transient amplifying cells and the basal cells. So the limbal cells, they are forming the transient amplifying cells and the basal cells, right? So the corneal epithelial cell layer mass, it is a complex result of three phenomena. What are these three phenomena? X, first is the X, which is the proliferation of basal epithelial cells. Then Y, which is the centripetal mass movement of the peripheral epithelial cells. Here are they proliferating, and then they are moving centrally. The centripetal is a mass movement of peripheral epithelial cells, and then the Z phenomena, which is the loss or the death. Then the death. So this is X, this is Y, and this is Z, which is the central loss resulting from the death and desquamation. Now these cytodynamics are responsible for the striking the verticillate, the vortex or the whir-like biochemical deposition which is seen in the Fabry's disease and the drug deposition keratopathies, which is like this. Once you see it, you will understand it better, but it is like something which is coming from the periphery towards the center. This is the pattern of drug deposition, right? Now this is a diagram which shows the X, Y, and Z hypothesis. Now this is limbus. This is limbus. In the periphery of the cornea, we have the limbus. Now these are the limbal stem cells which are being converted to the transient amplifying cells, right? So this proliferation is the X, their centripetal movement is Y, and then this desquamation, like they are developing from below and then they are going up. So this Z is the desquamation. Now this is the X, Y, and Z hypothesis. Now, thank you. In my next video, I'll be talking about the stroma and endothelium. Right?